Hello, my name is Ethan Gordon, a student in the Personal Robotics Lab at the University of Washington in Seattle, and I'm happy to present our work on adaptive robot-assisted feeding, an online learning framework for acquiring previously unseen food items. First, why assistive feeding? Eating is an activity of daily living, or ADL, which is a task that everybody needs to do every single day. Unfortunately, many people around the world, including over 1 million in the United States alone, lack the motor control necessary to independently carry out ADLs. Caregivers do an amazing job here, but some care recipients report feeling rushed, embarrassed, or generally challenged by the lack of independence. Importantly, feeding is one of the most time-consuming tasks for caregivers, time they could be using on other tasks or as a break. Our long-term goal is to provide an autonomous feeding system, not to replace caregivers, but to make their time easier while giving care recipients increased independence. This work uses ADA, the assistive dexterous arm, a Canova Jaco 2 augmented with an eye-in-hand RGBD camera and force torque sensor on the end effector. We also leverage common accessories in assistive settings, such as the non-slide base for the plate. And here is ADA in action. Assistive feeding in general is a complex, multi-part task, which we divide into 3 interconnected problems. Bite acquisition involves getting the food from the plate or bowl onto the end effector. Bite timing involves waiting until the user is ready to receive the food. And bite transfer involves the actual handoff between the robot and the user's mouth. These problems are certainly coupled. For example, we use conventional silverware for acquisition in order to make transfer more intuitive for the user. Though for this work specifically, we focus strictly on bite acquisition, and even more specifically on acquiring arbitrary, potentially previously unseen food items from a plate. A key challenge is the diversity of food. There are more than 40,000 items in a typical grocery store. I haven't tried all of them, but somebody must be buying them. We cannot expect to be able to extensively test all of them in a laboratory environment. Additionally, food is really hard to simulate and model. It is not only geometrically deformable, like floppy spaghetti, but the topology can change during manipulation, like a cheesy pizza that breaks apart when it's picked up. Previous work tackled this challenge in a couple ways. Narrowing the scope to food items that could be picked up with a fork, it presented a limited action space of 3 fork pitches and 2 fork roll angles based on data collected from humans. Secondly, it decoupled the problems of food detection and action selection. The former was done with an off-the-shelf model, RetinaNet, while the latter used the custom skewering position action network, or SPANET. The idea is that using this small set of high-level strategies would allow SPANET to more easily generalize to previously unseen food items. One limitation of this approach is that the small, discrete action space leads to very dissimilar actions. Therefore, choosing the wrong action is very likely to result in a failed attempt. For example, if a banana slice is picked up with one of the more vertical fork pitches, it is almost always going to fall off the fork before the robot can bring it to the user. Similarly, a shallower approach is unlikely to actually pierce a baby carrot. Additionally, while SPANET did do a good job generalizing to food items with optimal strategies similar to previously seen data, it had trouble with food that was completely unlike what it had seen before. For example, looking here, we can see that when a particular type of food is within SPANET's training set, it will correctly select the optimal strategy when given new examples of that food. But when we remove a food type from the training set, SPANET performs well on some food items, the one which were similar to other foods in the data set. However, some foods, like banana, were so different from the rest of the foods in the data set that SPANET ended up performing even worse than random. We would expect SPANET to have trouble with similarly dissimilar foods, like potato salad or spaghetti. Since, as discussed before, it is difficult to simulate food, and it's impractical to train SPANET on every type of food in existence, we would like to leverage online learning to have ADA better adapt to each user's diet on the job. But of course, online learning is a very general term. To be more specific, we can model bite acquisition as a contextual bandit. The contextual bandit setting is an extension of the multi-arm bandit setting. Think of each action as a slot machine, or one-armed bandit, with an expected payout that is potentially related to some context. I like to think of the context as a billboard behind the slot machines that changes every time you pull a lever, but I'm not much of a gambler. Importantly, you only observe the payout of the specific action that was taken, unlike more traditional supervised learning where you would be able to see a full loss vector. For those familiar with reinforcement learning, this is equivalent to an RL problem without transitions, or a time horizon of 1. More specifically, we can model our problem as a linear contextual bandit with stochastic rewards. The last layer of SpaNet happens to be a linear layer, so we can freeze the first n-1 layers of SpaNet after training as a sort of featureizer, turning the RGBD image of the food item into a context vector. We can then use this linear model to select a single action and observe a binary loss for that action. Definitions. We say that we receive no loss if we manage to pick up a food item and it stays on the fork for at least a few seconds, long enough to start manipulating. Otherwise, we receive a loss of 1. Finally, we take that loss and update our linear policy with ridge regression. The key to solving the contextual bandit setting is to manage the trade-off between exploring potentially suboptimal actions and exploiting the actions that we know work. Formally, the goal is to minimize cumulative regret, or how well our policy performs compared to how it could have performed if we were omniscient and knew the optimal policy from the beginning. One strategy, epsilon greedy, makes the trade-off explicit. The robot will explore, as in choose a random action, with probability epsilon, and it will exploit the best action so far with probability 1 minus epsilon. While the scheme is simple, it is also empirically competitive with a properly tuned epsilon. Another strategy is linear upper confidence bound, or LinUCB. It leverages the fact that we are using a linear model and the assumption that our rewards are stochastic as opposed to adversarial. In such a setting, it can be beneficial to be optimistic, assuming that an unknown action is potentially good. We do this by constructing a confidence interval around the expected reward for each action. The width of this interval is scaled with an exploration parameter alpha, but it will shrink as we take an action more often and become more confident in our reward estimate. The action with the highest upper confidence bound is chosen, which implicitly handles the exploration-exploitation trade-off. Putting all of this back into our framework, we have a system that hopefully does a better job adapting to previously unseen food items. To recap, we still have RetinaNet to perform object detection. The cropped image is passed to a frozen SpaNet that outputs a context vector. Our linear model outputs an expected reward for each action given that context. We follow an exploration strategy like epsilon greedy or LinUCB to select a single action from that information. We take the action, observe the binary reward, and use that reward to go back and update our linear model using ridge regression. Before we could test it out on the robot, we had to get some hyperparameter tuning out of the way. Doing a grid search on the robot with real food would have taken way too long, and not being able to know the optimal policy or the full loss vector, we wouldn't have been able to use cumulative regret as an evaluation metric anyway. Instead, we used SpaNet's test set as a validation set for the linear model. For each attempt in that data set, we had the image of the food item, the action the robot took, and whether the robot was successful or not. We could impute the full loss vector using a doubly robust estimator. We start with a guess that the expected loss for a given action on a given type of food was the average loss across all attempts with that action and food type. We can then remove the bias from this guess at a cost of higher variance. This left us with a validation data set of context and loss vector pairs that we could use to evaluate a given policy with respect to cumulative regret. Two hyperparameters, the dimension of the context vector and the L2 regularization parameter, only affected the performance of the linear model, so they were tuned with batch learning and traditional cross-validation. For the exploration parameters, epsilon and alpha, we performed an online rollout over the whole validation set and kept the parameter which exhibited the lowest cumulative regret. With the hyperparameters tuned, we used our first on-robot experiment to see whether the linear model was rich enough to distinguish between multiple previously unseen food items. We started with a SpaNet featureizer trained on everything except for grape, apple, and banana. 3 foods chosen because they both look dissimilar and have optimal actions with completely different fork pitches. Our linear model started out completely untrained. We then cycled through these food items for a total of 60 attempts, 20 for each food item, updating our linear model after each attempt. And here are the results of that first experiment. Each line represents an exploration strategy. Greedy, epsilon greedy with epsilon equal to 0.1, and LinUCB with alpha equal to 0.01. Since we cannot know cumulative regret in the real world, we instead report cumulative loss, synonymous with the cumulative number of acquisition failures. While there were sporadic planning and perception errors throughout the experiment, the vertical line shows the point after which each exploration algorithm discovered the optimal action and only performed that action for the rest of the experiment. We suspect that the naive greedy algorithm was competitive here because the linear model started uninitialized. There was no rut that the model needed to be kicked out of, so the extra exploration just led to slightly suboptimal performance. Regardless, the takeaway here is that within 10 total failures, the linear model was rich enough to determine the optimal action for multiple types of previously unseen food. The second experiment really dug into the question of whether this strategy could allow us to adapt to previously unseen food items in a reasonable amount of time without forgetting about previously seen food. We conducted this experiment twice, once with banana and once with carrot, with 3 trials per food item and exploration algorithm. For each experiment, we pre-trained SpawnNet and the linear model with all the food items that had optimal actions which did not match the one of our target food, so our previously seen food items. For each trial, we gave the robot 20 attempts at the target food item, followed by 5 attempts of a previously seen food item, followed by 5 more attempts with the target food item. And we recorded the cumulative loss for each trial. And here are the results. Each color corresponds to a different exploration strategy, and the range across all 3 trials is colored in, with the black line showing the average cumulative loss. The first takeaway is that no algorithm exhibited catastrophic forgetting. After 20 attempts with the target food item, all algorithms selected the optimal action for the previously seen food item at least 4 out of the 5 times. Secondly, with data from previously seen food weighing it down, greedy did not perform as well as the exploring algorithms. In general, LinUCB was very consistently outperformed both greedy and epsilon greedy in almost every trial. Here is a specific example of LinUCB learning the optimal fork pitch for banana after 20 trials. On the right, lumping together the roll angles for visual clarity, we can see the upper confidence bound for each action. The optimal fork pitch is in red. Notice by attempt 13 that almost every action is optimal. While this is still a lot of failures for a single meal, this upfront learning cost should be amortized over the lifetime of the robot, as it will not forget a food that it has now previously seen. With all that said, 10 or so failures per food item is still unacceptable for some of our potential users. Currently, the system only uses RGBD visual data. In the future, we hope to leverage additional haptic context from our force torque sensor to adapt even more quickly. In general, assistive feeding is a hard, multifaceted challenge. We have only been talking today about byte acquisition. Future work also needs to cover byte transfer and, crucially, the coupling between these two problems. If you're interested in giving this challenge a try, all of our datasets, code, and hardware is available to the public. All of them are linked from our hub at robotfeeding.io. A big thanks to my co-authors, Jiang, Matt, Tapo, and Sid, as well as the entirety of the Personal Robotics Lab for their support and guidance. And thank you for giving this a watch. Enjoy the rest of the conference.